Oh, I don't care about that. That one's not relevant. Ignore that. But yeah, thermal efficiency is 38.12%. QN is 3.21 times 10 to the 5th. You get a whole bunch of work. What's most important is data, Q in, Q out, and work done. That's it. But it solves everything else in case you want to put it down. No, I hate it. I don't know how. No, like graph. Oh no, there's no. It doesn't ask for it. Look at this. Graph section. I cooked up a program to solve number 2.
There we go.
This is an this is thermal efficiency. I should find every variable. It really tells you everything. And so if I show down the variables, the green ones are the given, and the blue ones are all calculated. Yeah, because you can call functions to summon, you can like summon, I say summon.
All right, cool. We made it to the final part of homework 1 through module 1. And I guess we'll do like quick logistic check-in. This week we've been working through like the module 1 homework. So along the way, like chapter 1, chapter 2, those are great references to take a look at. I have some places to focus on. So if you've been reading, great. If not, then this is a good chance to think about like what things are we talking about and how do these examples apply to that. Because mostly we've been like talking about how free body diagram is like giving us information about what to act, like how things are working. Sound good? Is there other stuff going on today? Like midterms or projects? Oh, okay, there's just like busy stuff. That's good. And then next week, goal would be like building quiz number 1. And then also like that project 1.
We did 2.11 was the skiing one. Okay, this one.
Oh yeah, I guess I'm jumping right into this, but did we have anything that you wanted to talk about with like that, with drag and skiing and the effect of mass on a skier? I kind of left it as like, yeah, you can do whatever you want from here, but I don't know if anybody was like, but I don't know what I want to do. Were there still questions? Do you want to take a second to like get back into it and I'll check in individually? Let's do that. And then we'll come back up, look at this next part. How did that last one, like 211, is there anything left that you're still thinking about?
I'm going to start trying to keep your business. I like very lossy math.
Okay. Yeah,
I literally wrote.
Yeah, bigger mass, faster speed. That makes
drag
sense.
force is negative and decreases with increasing mass. So bigger skiers have less drag and go faster. Thank you for coming to my TikTok.
Anything? No.
Bigger mass.
Okay. Yeah. Bigger is better.
Bigger mass, less air resistance. Since air resistance, or since like the less drag, since drag is negative, you want it to be a small value. So the bigger the mass, the smaller that negative value. So the faster
smaller, you go. Like it's kind of like the acceleration.
Smaller magnitude. Right? Yeah.
It's still the same force.
You want the value of drag to be as low as you can fail fast, and it gets lower as you.
Yeah, the acceleration term, the force per mass, because you end up with like a meter per second squared unit. At least if you're assuming force of drag is constant, you can increase or decrease mass. Drag.
Oh, the acceleration. Yeah. I see what
How's it going so far? I was asking about the skiing question, but whether
I'm getting into it.
okay.
Yes, kind of. I looked at the textbook a bit. It's actually like such a step up compared to physics one textbook.
Let me see.
Oh, the textbook is for free. Yeah. So like the first one is just like the same thing like before. If I just hit enter, these work. It's going to generate a graph. It's what the fuck?
Did you run the?
I did not run the plot.
Wait, how did you import the? How do we launch it?
I just typed in nano hub in my browser.
Oh,
The first problem
for shizzle.
is like the intro to Python. The first problem you can like copy paste it.
Oh my gosh, I do not remember. I do not remember.
Oh, this one, like you could code right here. You would say, insert cell.
No. I use the same password for every single website.
Say insert cell below, and then you have like a little block.
It's good. Like,
I still want to say it again. My calculator history is
Yeah, the goal is here to make a graph. So that's a great thing.
I put the most retarded.
Right.
Launch tools. Summon tools.
Sorry, I checked in with half the room. Half said, let's go. Other half says, let's go. All right.
Launch tool and then
Where do you think we should start with these different blocks to figure out what is, because our goal is like, what is x of t? Like how far does this block move as a function of time? So we're looking for, so where do we start? What do we do first?
I think we should review how to get to the Jupyter notebook to get to these drops.
Well, right now we don't need like a Jupyter notebook, but you can. We were just taking a look at that.
Oh, I'm slow.
But you can, like if you want to go to that Nano Hub,
insert cell.
then you could launch, like at least if you want to have like that problem with a Jupyter like Python block underneath it, we could do that.
But it can be on paper too.
Sorry?
It can be on paper as well.
Well, the plot should be. I've never seen a good hand-drawn plot, at least in the last 50 years.
Okay.
Because people used to be awesome. Like hand-drawn plots used to be exquisite, but they were so painstaking because you had to evaluate the function, use an actual like ruler to measure how far along the x-axis and y-axis. But they used to look really good. Now it's so much easier to get with, and especially we'll take a look at like ChatGPT today or any kind of AI, but some kind of tool. It's like, hey, I have this function. Can you plot it for 3 seconds for me? And even with that, it'll label our axes. It gives us some nice like starter code too. Okay, so we'll get to that. But first we need to know what we're plotting. So we need, if we want to plot it, then we need to know what is x of t. Give me my pen back, man. So where do we start for this? Oh my God, come on. Having all sorts of trouble. The microphone's not working, now my thing's not working.
Are you asking for scenario C? Which example are you insert?
Well, we need A, B, and C. And they're both kind of the same process of like getting to what is x of t.
Well, for C, we know the spread constant equation. We want to find like a force component.
So we know that it's like some kind of spring. Yeah. Where did we start for the first few problems? What's the main tool so far? Free body diagram. Yeah. Free body diagram. So here, like there might, especially this question C, you've probably seen that before, and you probably have some like, oh, I know. Maybe you do already know what the answer is, but it always helps to start with a free body diagram, and then prove to yourself that yes, indeed, this is the same problem that I already knew the answer to. My suggestion is always start with free body diagram. So let's start there. All right, so what do we have acting on? Oh my God. I don't know why the pen is giving me so much trouble today. All right, so take a second. What forces are acting on block A, block B, block C? What do they look like? Okay, nice.
Well, I just called it like F initial. What do you mean X? Well, it has an initial velocity. Yeah.
What does that mean?
Yeah.
That one's called a damper. So that one, like if you open or close a door, you know how it like swings real fast and then slows down. That's what a damper does. So, yeah, that's a good question. It's not everybody.
Did you see that your first cell runs import number is empty, and then your second cell was all the kinematic equations?
Yes. It's just copy and paste, like.
So you put plot.
Have you seen anything like this before? A damper? Do you know what that is? No? Okay. Well, I'm glad I'm asking. That's why we start with some free body diagram, because it's like, well, I know it's connected, but I have no idea what it's doing, like why it's there.
I didn't know what it was, so just like what they were doing. It's like, it's like, oh, it's an N. And here's the equation. It's great.
So there's different ways of like building a damper, but for the most part, it's like some kind of fluid and a piston. And when you move the piston through the fluid, the more you constrict the fluid to move around the piston, then the bigger the forces it'll create. But if you think about a fluid, if you're moving really slowly through the fluid, it's not applying much force to you. Versus moving really fast through the fluid, now it applies a lot of force. So first step for these kind of dampers are just linear damper. They're called linear because it's a constant times your speed. So the faster you move, the bigger the force. And it's always proportional that way. And if you get really into dampers, then you create like all these non-linear dampers and like frequency-dependent dampers, but we're not there yet. We're just doing straight up linear.
Yeah. For part C, is this spring at like rest value right now?
Ooh.
Like, is it stretched or compressed? Or
Is it stretched? Is it compressed? Yeah.
I'm gonna go with.
Does it change what your free body diagram looks like?
Yeah, it's gonna apply force in different directions.
All right.
Like hear me out. Like at the beginning, the string will spring out the box, but then it will recoil or whatever, and bring the box back.
Well, I assumed it's at like the rest value.
I think it's pulling the spring out.
But what if the spring was already pulling from the box to begin with?
Is the spring real?
And here, we'll do this. All right, so we skipped straight into the spring. It's okay, at least with a question. Because the question was, do we put a spring force to the left or do we put it to the right? What do you think? I've seen both, at least like when I was quickly walking around. To the left? Yeah. Yeah.
This one says like traveling to the right and then it goes to the left.
Okay, since we have an initial speed, so initially, like we're saying, like x equals 0. So spring is unstretched. So at time 0, there is no force of spring. But we do want to account for the fact that as we move forward, it is going to pull us back. Yeah.
I was just gonna say, you kind of intuitively know it's gonna pull back because it's a frictionless surface. So if the spring's not pulling it back, you're gonna push a box and it's gonna move forever.
Okay. But what about when it stretches all the way
When it
to the
stretches
end?
all the way out, the spring will pull it back, like to equilibrium.
So do we need, is it going to stay at equilibrium? No. Yeah, there's like some motion of like, people are saying, no, not like, no, more of bounce, bounce, bounce. It's going to keep bouncing, right? So it's going to move forward, then it's going to move backward. Do we need two different free body diagrams for that then? Do we need one for stretching and one for compression? Yeah.
Probably just one, and then like when it's going back, it's just a negative value for that direction.
Ooh, yeah, something's going to be negative when the spring is pushing the other way, right? So here, there's more than one way to deal with this, but I'll show you kind of the standard practice. We say that this force is kx and it's negative. So the idea here is that when x is positive, it's creating a negative force. When x is negative, now it's creating a negative of a negative, so it's a positive force. Make sense? And this is the standard practice. Is kind of like, imagine you stretch the spring in the positive direction. Which way is the force acting? And that's a nice way. Then you get one free body diagram that covers all the situations, stretching and compressing. Cool. Okay, so then what did... Actually, now I can copy things over, right?
Yeah, that's what I'm asking. Is there an initial force in the spring?
You mean on the box?
Yes. Yeah. Because like when it goes all the way to the end. Yes.
No, like when you, because it has initial velocity, it has initial force.
So I saw most people recognize that like weight and normal force are not affecting forward backward motion. So we can say that across the board, all three. Where do we want to go now? A or B? So C, I think we're good. What about A or B? Which one do you want to do next?
We don't need the initial force. You use the pushing. It doesn't matter because we have an initial velocity instead of a force.
Ooh, okay. Yeah, another good question. Does the initial speed, is that a force in our free body diagram?
It's not accelerating.
Because it's not really like a force. One thing you can do to think about it is like if you're considering the fact that yes, you need to apply a force to do that. The way people usually think of it is that at time 0, an impulse was applied. So there was some F delta t, which created mv. So now we have initial velocity. But it's not a constant force. It's like a spike at time 0, and then it's gone. So our free body diagram is just the things that are consistently there. But if you wanted to say that, then you could have like an FDT only at time 0. If you want to specifically say like I want to know what force was applied, but we don't need to. All right. What about for that damper? Which direction do you think damping would happen?
Opposite of motion.
Opposite of motion. Okay. So which way is that one?
So to the left.
To the left? Is it always to the left?
Yeah. Well, it's like friction. It's just friction, but like a different curve. So it's always going to be opposite motion.
Okay. Yeah.
That's what
We're saying the same thing. I'm slow.
So in this case, we can do the same thing that we did with the spring, of saying that it's B times V, considering positive V. So for a positive velocity, it's a negative B times that velocity. And if it flips around and now it's moving backwards, in this case it won't do that, but if it did, like if we had the spring and the damper connected to each other, which is a more typical setup. It's like spring mass damper setup, so that you have like you have control over the motion. That's how all of our shocks in cars work, cars, bikes, even doors. Like that door has a little torsion spring inside of it and a torsion damper, so that if it spins really fast, it slows it down. Cool. Nice. That's a nice part about like linear springs, linear dampers. It's in the opposite direction. Just consider positive. All right. So now, what about friction? What do we have to do there? Same thing? What is the force of friction though? Is it proportional to speed or displacement? It's just a constant like mu times n, right? So we just have like mu times n. And technically, like if we want to get specific about it, then it's also in that direction of motion. So if velocity changes, then that would change. So negative, in that negative like EV direction, something. But it's always opposing that motion. And let's make these all consistent. So I'm going to get rid of this one. Get rid of that. What does the kinetic diagram look like? Because in this case, they're all kind of the same kinetic diagram for A, B, and C. What is that one describing? Yeah.
Is it just describing it's like velocity instead of forces?
It does have to do with velocity, yeah. But it's not, at least for a kinetic diagram, it's not describing like where velocity is pointing. It's another term. What is sum of the forces? Sum of the forces equals mass times acceleration. So our kinetic diagram is describing mass times acceleration. So where is MA pointing in all three of these cases?
To the left.
To the left? Yeah. That is true. All of our forces are pointing to the left. So your mass times acceleration is just describing like what am I saying is a positive acceleration. So in this case, the answer will be, it's always negative in all three cases, but the actual, oh my god, need this pen back. Like in order to set up our differential equations, we're always saying like MA is the positive, because it's just a description of like, if I measure acceleration and it's positive, this is the way that it would go. So in this case, we have a constraint that it can't move up and down, but it can move left and right. So it is going to be, the acceleration will be to the left, but what we'll end up doing is saying that MA is a negative value. And all of that is like it's a good way to keep track of forces, because if your acceleration and your forces are all in the same direction, then it's like an unstable growth kind of system. Like if MA equals V, then the faster you move, the more acceleration you have, and then you like zip away. So most engineering systems have some kind of restoring force, something to slow it down, something to bring it back to equilibrium. It'd be nice if you do have like an unstable growth system, at least if you can control it. But if you can get free energy that way, that the faster you move, the faster you want to move, great, go for it. It'll be, yeah, free energy. Is this pen? Oh my god, this thing is driving me crazy. I want my pen back, man. Oh, that's not gonna help. All right, can't draw today.
Says the website's down.
Oh, the web. Wait, which website's down now? Oh, NanoHub is down? Nothing's working today. What? We just got in there. For snow day? Yeah.
It broke yesterday, but they couldn't fix it.
Really?
No.
All right, we'll get there. Friday mornings. All right, so we're trying to come up with three different differential equations. Because in general, we're always going to come up with some kind of like second order differential equation where m times d squared x dt squared is how whatever forces are applied. So this is our next step. So m I'll leave that one. So what are these three equations that we need to solve?
Wait. How do you write the notation for dx squared dt squared?
It's
Is it like d squared
d
x?
squared x over dt squared.
Yeah. So the t is
It's
squared
really
and then
weird.
d. I guess it should be d squared x, right? I put the I just put it in the wrong place.
Or you could do double dot.
Yeah, double dots are good.
Yeah, it's not my first person this one too. But like, Professor did everyone.
At least based on the like
Which person?
Yeah, so the Rizzi class,
only describing what it is.
But you put it in the grade.
I did the first one, so easy.
Oh, it's so good.
It's so measured.
It's 5
That's what I'm saying.
I looked at the website.
Yeah. What's that?
I've been
I've just been doing all the
The diffy you can't figure out.
I've been doing that. There's some memes as well. That if you want to show you can learn or watch it, it shows you to do step by step.
Wait, what topic are you on?
And like most
It'll show you. Like, she was lecturing, and then she was like, oh, that's all you're supposed to do. Like, I like 25 minutes of class.
I don't understand how to express d squared x over ct
Just do x with two dots, but why double press?
that might be
It's not
that would be like an extra.
What's your title?
This is x and x equals
It's x double.
That makes it confusing.
Now, because why that?
Look, what's up with mine?
This is why we do
We've been going like
Yeah, we
really
talked about
Well, this is diffy q now.
exact equation.
We're gonna get a separable result.
Since what acceleration is just a second derivative of position.
Negative f.
That's what I saw so far. Looking good? So part A, this one we've seen before in that, at least like our first kind of Python work. Like we had something sliding, there's friction. So how do we solve that first part A differential equation?
Is that like, sorry, is it mass times mu, or is it just mu?
I just wrote it out as like mass, mu, and g.
So mu times the weight force.
Like mu times w.
Oh, okay. Okay, I was confused. I couldn't tell if you're multiplying the mass by mu, or by, you know what I mean? Because it's a u and it looks the same.
Oh, u, as in like u is speed? Or?
No, I thought when you wrote u by itself was mu, and that the m
Oh,
was mass.
like an m times
Yeah,
a u,
so you
not a mu. Yeah, I know. I really need this pen back, but I think I got to restart my computer. Anyway.
Yeah, mine's just not connected.
So,
Not live.
Sorry.
in the hypothetical that Jupiter does not reboot within the day to plot the graphs, do we just draw?
Don't do a hand-drawn graph. Yeah, do anything like Excel, Google Colab, Desmos. A lot of people have done Desmos. Hand-drawn. I'm just trying to save like some time because hand-drawn plots take like an hour to make, and it's
I'm gonna do my
I mean, not if they're
Yeah.
bad.
yeah. If they're bad, then they're quick, but then you can't actually see what the difference is. Yeah, plotting is plotting. Like it's got to be like a nice. Oh, sorry. Woo. Long week. All right, what is x of a? What's that first? If we have a constant force applied, what does that tell us about acceleration? Constant acceleration. So constant acceleration is kinematic equations. And that's the whole point of like doing a free body diagram is like try to convince yourself that you can find a solution for that setup. So in this case, we set something up where mu n is a constant value. So now we know acceleration is constant. Force is constant, acceleration constant.
The damper changes with speed.
What is the t squared h over dt squared? That's just really
Oh wait.
That's A.
But like, what is it? What is it?
The second derivative.
Oh, a position?
Yes.
Oh.
That's by definition acceleration.
Look, I looked the right day.
Can we jump straight into xb? Is there a way to get there? What do we have to do here?
Like integrate somehow.
Gotta like do some kind of integral, right?
Yeah, look at the textbook. The equation's like e to the something x.
Yeah, some kind of exponential sort of curve, right? Why can't I? I want this pen back so bad.
Wait, no. Do we take this and just apply it each time?
No.
Why not?
Because the damper kind of changes the velocity.
I don't know. I thought it had batteries. I had just replaced it.
You have to insert batteries into it, or is it exponential?
No, insert. I mean, I can try a new one. I think it's some kind of connection issue. Connect. Come on, connect, man.
Plus m times v0 over b multiplied by 1
Ah,
minus
all right.
yes m v0. Yeah.
Times.
I thought it helped for like math.
To the what?
E to the negative e over m times the change in z.
So another way we could look at this is like dv dt negative b over m v, like this.
So the change of velocity for the second time, for only the second one, is negative b. Wait, that doesn't really make sense.
What doesn't make sense?
Because I thought we were trying to get acceleration.
V over T is acceleration. Change it along.
And then it deleted my last thing, but that's all right. So if we get multiply both sides by dt, divide both sides by v, now we have two equations that are only a function of one variable. V's on the left-hand side, T's on the right-hand side. Do you know how to deal with that? Yeah, it seems familiar. Something.
Is this just like a separable individual?
Integrate both sides. So we did. So right now we separated them both.
We did like a similar thing with physics too, with like passage.
Oh,
Not that.
What are we trying to get from this equation when we integrate?
Then we'll have v of t. God, that's ugly. Not great, but it's there. So the goal is, at least first step, if we can get v of t, now we've got velocity as a function of time, which is dx dt. So we can integrate one more time. So every f equals ma equation is always going to give us second order, so we have to integrate twice if we want to find what is position as a function of time. And that's kind of what we're figuring out here, slowly but surely.
Mm-hmm.
I always like to go, ooh, excuse me, make it exact integrals, like go from v0 to v of t. And then this would go from 0 to t. The nice part about doing exact integrals is, like, normally you learn taking an integral, you have to add a constant. But if you do exact integrals like this, like give it bounds, then the constant disappears because you always subtract it out. Like v of t minus v0 evaluated. So give this a shot. I'll check in.
You get natural log. Yes. Natural log of absolute value of bt minus natural log of v initial. Well, you subtract natural log, you really get. Yeah. You take natural log of bt. No, wait. You're taking. So what you do is you take natural log of bt over the initial.
So natural log bt over
Yep, I have that after that. So that equals
negative b over
negative b over t
plus c.
No.
Oh wait, no, it's
No, do not add c to a definite integral.
Oh, Rizzy was working on some math. Was explaining some theorem, and it turns out there was 6 different C values showing up. Yes.
What did you learn?
I remember I made it in my notes. There was like some theorem.
What? It's VO and VT.
Which one did I talk to VO on?
VT's on top. Yeah, I found 6 different C values.
Oh, and then what? Do we exponentiate? So we wanted to say VT equals, right? If that's the case,
Yes, we wanted to say VT equals something.
in that case we just exponentiate. Right, so then we have VT over V initial equals E to the negative E over M times T.
How's that? Something
V of T equals
get there eventually?
Oh, separate equations.
Oh, times that v0, right?
Wait, so you do this? I have VT equals V initial M negative D M. That's what the E to the power. Okay, so then we integrate it again. E to the negative dm over t is what I get.
Yeah, so you end up with like log of v over v0 equals negative b over mt. So then e to the log ends up just v of t equals that v0. Cool.
I misspoke. My bad.
So now we still have like left-hand side is like dx dt. Right-hand side is just a function of t. Sorry, yeah. That one, it could be 0, but in this case, it's like an initial, we have an initial like 10 meter per second speed. But it could be 0. Then we have like a pretty uninteresting solution though, because it's just v of t is 0 because v0 was 0. Not as fun.
We're gonna end up with like a sine or a cosine.
No, but you use the same process to solve for the x of t for the string equation, right?
This is not running.
Oh, there's always counts.
By the way, when people say it's, what's that phrase? It's like, it's not rocket science. You can tell them you know how to do rocket science. It's like, I'd rather do rocket science than do it.
So wait, now we're taking.
Is V of t.
So since v is dx dt, since we're only moving left and right, so if I know the change in x, I know what velocity is.
You know, I realized when I transferred, my base we didn't do calculus. That's why I have no idea. Oh, you guys just know what's going on? Okay.
We barely did calculus in physical. Like the teacher did all the calculus for us. At Stanford.
My physics class was like nothing. I think the most complicated thing we learned was like.
So now we've got another separate equation. Right-hand side is all t's, left hand is all x. Integral of dx is x, well, x minus x0.
And the water pressure.
Really?
We're running out of time.
Yeah.
That t is in the numerator, right? It's just not in parentheses.
Yeah. And I can go 0 to t. The only tricky part here is that e to the 0 is not 0, it's 1. So when we evaluate like e to the something t minus e to the 0, it's actually like minus 1. Give me one. Man, yeah, NanoHub is really holding us back today. Is Husky CT working?
It's like a soft boot video.
Yeah, I gotta do that.
If you get that software, the software can help a lot.
Yeah, download. It's free. You have to restart your computer though.
Because it's old.
Yeah.
You saw it, you saw it.
I was thinking, I was like,
Solid.
what is he talking about? Restart your computer, it's still not here. And then like 5 minutes after I restarted, it popped up on my screen. I was like, oh, okay.
Oh, and then this one, we're supposed to finish today, but we're not going to finish today. We need more time. At least I think we need more time. Is that worth doing another day? Let's do like Tuesday. That's what I want to double check.
No, I actually
Let's do that. Push it back. Yeah, so that we actually have time to do stuff. Let NanoHub catch up to us.
acceleration is dv over dt, and v is dx over dt.
Yeah. All right, we'll get there. We got time.
Just one of my gripes with calculus is before like integrate this, integrate that, it's like what are you actually doing? Like what does that mean?
Yeah, here.
Now this makes sense.
This gives a meaning. Whoa, that's good.
Yeah, here like we actually like it's a process, but we're making steps towards finding an answer. Like, what is this answer? Why is it important? All right, I'm gonna restart this computer, man.